Hello everyone. Today I will be discussing about simulating a 2D Taylor-Green vortex using pseudo-spectral methods, and my name is Islam. Hopefully you will enjoy it. So I will go briefly about what TG vortex is, the numerical methods employed, and discuss the results of this numerical study. So what is Taylor-Green vortex? It's nothing but an unsteady flow of a decaying vortex. So when you have large, unstable, and highly energetic eddies, they break down in a cascading fashion into smaller and smaller eddies, smaller and smaller length scales, and eventually die out due to viscous dissipation, according to forward cascade. And so this Taylor-Green vortex is a canonical turbulent flow that has an exact closed form solution of the Navier-Stokes. And in Cartesian coordinates, you can find the analytical solution to be what's given in the bottom of the slide. And to the bottom right, you can see how the vortices should look like. Okay, so the domain has been discretized in Fourier space using Fourier basis functions. The temporal discretization has been implemented using RK4 scheme, and the incompressibility has been enforced using a fractional projection step method. We can all appreciate the 2D Navier-Stokes. You have the continuity equation and the two momentum equation in the x and y directions. So as you can see, this will be Fourier transformed. So the Navier-Stokes Fourier transform would look something like that, where enforcing the incompressibility would require that the transform velocity is actually orthogonal to the wave number vectors. So using the projection operator, which is often denoted as that P in the bottom right, the Fourier transform pressure is successfully eliminated. Okay. So in Fourier space, eliminating the pressure term after you take the divergence of the Navier-Stokes, also in Fourier space, you obtain this final momentum equation of the Navier-Stokes and the continuity equation, also in Fourier space. And so you use this to predict your velocity, and then you update the velocity using this next step in the projection in the spectral space. And so the continuity would look something like that. And so once you have the predicted velocity in Fourier space, you can correct it using the divergence-free condition. So now you have velocity that is actually divergence-free. Some of the nuances of handling the nonlinear term, you could just keep that as in its conservative state. And so you can just take the average of the right-hand side. So in Fourier space, all the components have been transformed, and the wave numbers are discretized, such as the following. Gauss-Lobato points are used to define the collocation points for solving the PDEs, especially for domains with boundary constraints. But you can also implement this for periodic boundary conditions, which I actually use. The velocities are initialized using periodic functions, sines and cosines, and so using Gauss-Lobato points have numerous advantages, such as handling the boundary conditions, minimizing interpolation errors, which actually dictates spectral accuracy in space, and it actually improves their numerical stability and reduces aliasing errors, which is common when you're actually resolving your flow in spectral space. The frequencies could overlap each other. And yeah, so you transform the velocities, and you can also correspondingly have the inverse Fourier transform of the velocities, and correspondingly you can also do it for the spatial derivatives of the velocities. As I mentioned before, in the RK4 scheme, you choose the weighing coefficients that you use to update your velocity at every time iteration. So RK4 would require you to iterate 4 times. Now I'll be talking about the results. So this is how the velocity field actually looks like for a domain of 32 by 32. and this looks very close to what the analytical solutions will give you. I have also computed the normalized velocity profile in the center line and matched it with the analytical solution, and this is how it would look like. It looks periodic. So this is the spatial convergence, and as you can see, it exponentially decays. And temporally, it also decays on the order of 4 as expected when using a temporal discretization scheme such as the RK4. So as you can see, the vortices would evolve like this. Let me play it for you. Let me actually fast forward this. So this is for like 50 time steps. For any decaying turbulence, the rate of change of energy would actually equal to the rate of dissipation, since there is no production term, and so you can get this ODE. To see if they're equal, this is how it looks like, and as in fact the rate of change of energy over time is actually equal to the rate of dissipation. So all the energetic eddies are actually broken down to smaller and smaller eddies and eventually die out because of viscous dissipation. And as you can see, these two data overlap just perfectly. And so this is the literature that has been used. Thank you so much for attending, and hopefully you guys have enjoyed it. I know I'm slightly over 5 minutes, but yeah, I should have recorded this differently, but here we are. Thank you guys.